Hello everyone, my name is Frans Marcelino Purba. Now I will present the result of my work is modern alloy production. Supporting lecture Professor Dr. Tjokorda Gde Tirta Nindhia, STMT. Metallurgy Mechanical Engineering Study Program, Faculty of Engineering, Udayana University. Reference Metallurgy for the non-metallurgists, second edition edited by Arthur Syriaga. Topic. The first is topic is facts of alloying of solidification. Two solidification structure. Three is melting furnace. Four is molten metal processing. Five primary producing casting. Six foundry casting. Seven non-ferrous casting alloys, and eight is no powder metallurgy. The manufacture of modern alloys is accomplished using a wide variety of melting, casting, and fabrication techniques. The selection of a specific manufacturing process depends on the alloy system under consideration, the form of the product to be manufactured, the condition in which it must be provided, and the properties that it must possess in order to be used effectively in the intended application. Effects of alloying on solidification. Solidification of pure metals. When a pure metals begin to melt, the solid liquid mixture stay at the melting point temperature until all of the solid has completely melted. The amount of thermal energy needed to complete the transformation from solid to liquid is defined by the latent heat of fusion of material. A slightly different cooling curve can be observed when the molten metal includes some minute solid impurities, such as such. A slight different cooling curve can be observed when the molten lead includes some minute solid impurities, or such as particles of gas or small pieces of the reactory brick used to line the interior of melt furnace. This unfurnace promotes solidification by serving as nucleation sites such that free moving atoms can insert themselves onto the impurities. Therefore, only some undercooling or supercooling might occur when the melt includes such impurities. Characteristic cooling curves A for the metal with no free metal present, and B for pure metal with foreign metal present. The presence of impurities should reduce the amount of supercooling because impurities produce a strong nucleating effect, but the melting point itself remaining unaffected. C is typical cooling curve for a solid liquid solution alloy, not the freezing across over a range of temperatures. Aluminum silicon phase diagram with a gas microstructure of alloys with various composition above, below, and near the authentic composition of prior 12.6% Si. Alloys with less than prior 12.6% Si are referred to as hypothetic, those with close to prior 12.6% CSI as authentic, and those with over prior 12.6% SI as hypothetic. This is a particularly important consideration in aluminum silicon alloys, which have been used for decades in the automotive industry for casting engine blocks. Aluminum silicon are used in the application primarily to reduce overall potential weight and to improve fuel economy. The freezing range is strongly dependent on the silicon concentration in this alloy. Next is solidification structure. The solid-liquid interface during solidification normally exhibits one of three types of crystal growth in the liquid: planar, cellular, or dendritic growth. Like the picture, as known is the picture, Dendritic growth is a further modification of cellular growth in which the spikes develop sharp protrusions at still single undercooling and high growth velocities. The cells grow into rapidly advancing projections, sometimes of complex geometry. Like the picture is effect of undercooling solidification structure. Thermal supercooling, cellular growth as illustrated in the picture occurs when the advancing planar solid-liquid interface becomes unstable and a small spike appears on the interface that then grows into a cellular type structure. The planar surface becomes unstable because any part of the interface that grows ahead of the remainder enters a region in the liquid that is lower temperature. The initial spike that from remain discrete at first because they grow by solidification. They release their latent heat of fusion into the adjacent liquid, causing a localized increase in the temperature. Consequently, parallel spikes of almost equal spacing advance to into the liquid. Like the picture is transition from planar to cellular growth. Geometry. Dendrites are small crystalline needle shapes like pine straws, so named after the Greek word dendros. For the dendrites have a primary arm with secondary and tertiary arms that branch from it. The spacing of the secondary arms proportional to the rate which heat is removed from the casting during solidification. Like the picture, scanning electron micrograph of dendrites in the central region of a steel casting. Original magnification 46 times. Solidification zones. Metal cast into a mold can have up to the 2 or 3 distinct zones or types of grain growth. A chill zone is a zone containing columnar grains and a center liquid grain zone. However, it should be noted that all three zones do not always occur that to picture, and these are a chill zone, and this a zone containing columnar grains, and this a center liquid grain zone. Ingot structures. A is sketch of steel ingot showing chill zone, columnar zone, and liquid zone. B 1100 aluminum ingot without an liquid on zone in the center. C and C is cast 1100 aluminum coarse grains top and with grain refiners at the bottom. Melting furnace. Melting furnace are industrial devices to melt porous materials such as metals, glass, or ceramics. For casting, welding, or other manufacturing process, the furnaces are crucial in industries like foundries, metalworking, glassmaking, and ceramics production. They come in various types and configuration depending on the specific requirement of the materials being melted and the production process. Here are some common types of melting furnace. The first electric arc furnace, where gas furnace uses electric arcs to generate heat, melting scrap metal or other materials. They are commonly used in steel making and can heat ship. They are commonly used in steel making and can achieve high temperature quickly. 2. Induction furnace. Induction furnace use electromagnetic induction to heat and melt metals. They are efficient and commonly used for melting ferrous and non-ferrous metals like iron, steel, aluminum, and copper. 3. Crucible furnace. Crucible furnace consists of a container or crucible made of refractory material where the material to be melted is placed. They can be heated by various methods, including electricity, gas, or even traditional fuels like coal or wood. These furnaces are pressing and used for melting smaller quantities of metals or for specialized applications like jewelry making. 4. Cupola furnace. Cupola furnaces are used primarily in foundries for melting iron. They work by burning coke or a type of coal to produce heat, which melts the iron or and other additives. Blast furnace. Blast furnace are like vertical furnace used primarily for smelting iron or to produce pig iron, which in the then future process into steel. They operate by consequently feeding iron ore, coke, and limestone into the top of the furnace where a blast of gas air is burned in from the bottom. 6. Gas furnace. Gas furnace of use naturally gas or propane as a fuel source to generate heat for melting metals. They are commonly used in small-scale operation or where electric is not readily available. 7. Oil-fired furnace. Oil-fired furnace used for oil as a heat source for melting metals. They are less common than electric or gas furnace but can be used in situations where other fuel sources are preferred or more readily available. The size of melting furnace depends on factors such as the type and quantity of material to be melted, energy efficiency requirements, cost consideration, and environmental regulation. Each type of furnace has its advantages and limits, and setting the right ounce is crucial for optimizing the melting process. And assuring product quality. Molten metal processing. Molten metal processed molten metal processing. Molten metal processing and handled in various ways depending on the alloys and melting practice that are used. Melting is a basic way of combining elements for the purpose of alloying, and the overall chemical composition of the molten alloy must be carefully controlled and processed before casting can take place. Fluxing. Fluxing of molten metal is often the first step in obtaining a clean melt. Fluxing is a term commonly used in foundries and melting departments that refers to molten metal treatments from the addition of reactive chemical compounds or inert gases. The various functions of molten metal fluxing additive, either singly or in combination, include: the first is removing inclusion impurities or dissolved gases from the melt. 2 is preventing excessive information of solid phase inclusion. 3 is preventing or reforming oxide buildup on furnace wall. And 4 is injecting or distributing alloy constituent. The type of flux depends, of course, on the composition of the melt on brick storage and iron and steel making. For example, the function of fluxation is twofold. The first is to render the high melting refractory oxide impurities visible and separable from the molten metal, and second is to provide a medium with which the impurity elements or compounds will combine in preference to the metal. In particular, fluxing is used extensively in controlling dust formation and removing oxide from aluminum melt and melting furnace. The basic types of aluminum fluxer are: the first is copper fluxes, designed to produce a barrier or blanket on the surface of molten aluminum. 2 is drawing fluxes with melting action that promotes collection of aluminum. And 3 is melt cleaning fluxes designed to remove aluminum oxides from the melt. And 4 wall cleaning fluxes specifically designed for the softening and removal of excessive aluminum oxide build up to across on melting furnace walls. Fluxing of other non-ferrous alloys includes: the first is fluxing of magnesium alloys using salt fluxes or inert gas as a copper. Two is fluxing of copper alloys to remove gas or prevent its absorption into the melt, to reduce metal loss and to remove specific impurities and non-metallic inclusion. Three is fluxing engines alloys, which chloride containing fluids that from fluid/converse, which can be used to minimize melt loss if they are carefully steamed for the melt before curing. Primary production casting. Foundries also require the use of ingots that can be remelted, or sometimes called pig ingots, to provide specification complaint composition. Other defects that may form in a ingot during casting and solidification that roll result in cracking during forget rolling or extruding include metallic impurities, non-metallic impurities, slag, dross, and flux inclusion, inferior microstructure, segregation, surface cracks, and internal cooling cracks. This picture is automatic stacker of ingot for foundry remelting, contrasty if like metal A. Next is static ingot casting. Several ingot casting processes have been designed and developed for downstream manufacturing process. The most common is static ingot casting, where molten metal is poured into a vertical open-ended mold. Continuous casting process. Continuous casting may be defined is the continuous solidification and withdrawal of product from an open-ended shaping mold. And like this picture, the solidification ingot may be handled in several ways. For instance, while the ingot is growing in length, it can be dragged into a holding pit. At the appropriate time, the continuous caster can be shut down and a section of the ingot carpet and remove it from the holding pit. Then the process can be restarted. This is known as semi-continuous casting. In another process, the product is behind the fixture so that emigrates horizontally. From the casting machine, with the setup, casting time is limited only by the amount of liquid metal that can be supplied to the caster. The product can be cooled to any desired length, or it can directly into other processing equipment. Specific grades of aluminum, stainless steel, and copper are commonly produced using this method. Foundry casting. Subcasting in metals can be divided into three broad categories. The first is casting with expandable mold, or such as sand, plaster, ceramic, and graphite molding. Second is casting with reusable or permanent molds. And three is casting with reusable or permanent molds with high pressure metal injection of the metal into the mold, die casting, squeeze casting, and semi-solid processing. Casting with expandable molds provides tremendous freedom of design in terms of size, shape, and product quality. Expandable mold methods classified further as either the first is expandable molds with permanent patterns, and second is expandable molds with expandable patterns. When permanent patterns are used to mold USB spreadable into two or more parts in order to permit withdrawal of the permanent pattern. The permanent pattern is the negative or mirror image of the part to be cast, and the patterns are used to form the cavity for the cup or top and drag or bottom section of the mold. After the patterns are removed, the cup and drag selection are sealed together for casting. Like the picture And this picture a major component of a sand mold. A is pattern assembly for cup and drag selection, and B is cross section of mold which is called non-ferrous non-ferrous casting alloys. Aluminum casting alloys. Aluminum casting alloys are the most versatile of all compounds. Foundry alloys and granules have the highest castability ratings as casting materials. Aluminum alloys have case polyfibril characteristics. The first is good rigidity for filling dense section. Second is low liquid temperature relative to just required for many other metals. Three is rapid heat transfer from the molten aluminum to the mold, providing shorter casting cycles. 4 is hydrogen is the only gas with appreciable solute in aluminum and its alloys, and hydrogen solubility in aluminum can be readily controlled by processing methods. 5 is many aluminum alloys are relatively free from hot salt, taking and turning tendencies. Chemical stability. And 6 chemical stability. 7 is good as gas surface finish with a lustrous surface that super few or no blemishes. Next is magnesium casting alloys. Magnesium casting alloys of all types have found used in many commercial applications, especially where the lightness and rigidity are major events such as phone chainsaw bodies, computer components, camera bodies, and certain portable tools and equipment. Magnesium alloy as sand casting are used extensively in aerospace components. Molten magnesium alloys have a very low viscosity, allowing the material to flow long distance and through narrow mold capacities. Zinc casting alloys. Die casting is the process most often the shaping zinc alloy. Sand casting, permanent mold casting, and continuous casting of zinc alloys are also practiced, but account for less than 10% of zinc casting tonight. All processes are based on the same family of alloys like the special composition of zinc casting alloys. Order metallurgy. The general types of automation process encompass a number of industrial and research methods. Industrial method includes the first is two-plate automation, where a liquid metal is broken up into droplets by impingement of high-pressure jets of gas, water, or oil, like picture 28A and B. Second, centrifugal automation, where a liquid stream is diverted into the droplets by the centrifugal force rotating this cup or electrode, like this picture 28 sheet. Next, three vacuum or solid gas automation, where molten metals is super saturated with a gas that causes automation of the metal in vacuum, like the figure 28G, like that. Next, in ultrasonic automation, where a liquid metal film is agitated by ultrasonic vibration in picture 28E. Next is gas atomization. Gas atomization. Gas atomization process generally produce powder fractures that differ from those produced by water atomization process in terms of their geometry and surface chemistry. Gas atomic powder are typically more specialized in geometry and possess a lower surface oxygen content than their water atomic counterparts. Gas atomization difference from water atomization is several aspects rather than being determined by the processor of the medium and water atomization. It is found that the gas to metal ratio is the dominant factor in controlling powder fracture size, with median fracture size being related inversely to the square root of the gas to metal ratio. Gas atomizing needs also come in much wider of design than water atomers and are classified in either confit or free fall nozzle configuration. Like this picture is two fluid automation with this picture A, free fall design gas or water, and B, functional B nozzle design gas only. Design characteristic A, and A is angle formed by free falling molten metal and atomizing volume. A, distance between molten metal and nozzle. D, diameter of contained molten metal nozzle, and P, pulsation length of metal nozzle. Okay, that's all my presentation. Thank you very much and see you next again. Thank you.